we were talking about discrete complex exponential in the last one. This is a very important property, which is that for discrete complex exponentials, frequencies k and negative k give conjugate. Why is that erasing? Give conjugate exponentials. So I don't know why I wrote that in English. It doesn't make sense. But the idea is that if I have a complex exponential ekn, it is going to be the same as e minus kn, but we conjugate. Okay, and reminder, conjugate does two things. Conjugate says a plus bi. Conjugating it turns into a minus bi. Or if you have if you instead represent this as e to the I r e to the I theta, then this turns it into r e to the negative I theta, or I times negative theta. Okay, and you can see this geometrically. I think I talked about it in the intro to complex numbers video, but just to clear it up, right? If e to the I theta equals cosine theta plus I sine theta, e to the minus I theta, if we plug in minus theta here, cosine theta minus theta just becomes cosine theta, but sine is odd, right? So sine of minus theta would become minus I sine theta. And so you can see that these two are conjugates of each other because we just take a plus bi and we turn it into a minus bi. So that should be clear. Okay, so this property is like relatively straightforward, right? We can prove this pretty simply. So here could be the proof. We could say, okay, let me see what this e minus kn looks like. So again, just using the definition of a complex exponential, that's 1 over root n e to the j 2 pi negative k little n over big N. That just comes from the definition of what a complex exponential is. We can, move out this negative and turn it into 1 over root n of e to the minus j 2 pi k n over n. And then you can see that this is a pretty straightforward property, right? If we know that a negative in the exponential means we've taken the conjugate of the original. So this means taking e to the j 2 pi k n over n all conjugate, right? And so because to take the conjugate of a complex number, you make its exponential negative. So that makes sense. We showed that here. And then this inside part is exactly just e to the k e k n, right? Because it's a positive k here. So complex way of proving a kind of simple idea, but that's going to be very important in proofs, and it's going to come up. Okay. So what that kind of means is that opposite frequencies, right? What does it mean to take a conjugate? It means your real part stays the same, but your imaginary part is changing. So opposite frequencies have the same real part, so same cosine, but different signs. Their sign components, imaginary components, flip sign. It's just kind of a sort of that's a way of saying that. Look, if I have a bunch of frequencies, right? So let's consider our set 0, 1. Remember we said we'd keep n of them total. So let's say I decide to choose it like this. Okay, these are my n frequencies, right? Remember from the last video we said that any more will just be repeat. So the next one here, n over 2 plus 1, would be an exact repeat of this one right here. So we don't need them. So I'm going to get rid of it. Hello. I'm going to get rid of it. Okay. So those are our n frequencies. But what we've shown here is that even more, we don't really even need to keep all of these n over 2. They're not all distinct, right? The only ones that are distinct are these right here. Because this guy is a negative frequency of this guy, right? If this guy is k equals 1, this guy is k equals negative 1, and we don't have to remember what the value is for this one because we can just conjugate whatever the value was for this one. So for k equals negative 1, if we had, we knew what a ekn was, right? We just need to take the conjugate and we get this one. Okay, so this means that especially for real signals, right? Because if your signal is real, right? It's a plus bi, where this b term is 0. So it's just a real number. So the conjugate of your signal is a minus bi, but there's no imaginary part. So real parts, their conjugate is the exact same. So for real signals, we really only need to keep these many components. Okay, and that's an important, concept to understand in terms of memory, and it also helps you solve problems, because we don't this k equals 0 has its frequency, n equals 2 has its frequency. All of these have their own frequencies, but other than that, everything is based off of, this set of signals. So the key idea is, even though we have n components here, we only really have we have n over 2 plus 1. So that's all of these, right? We have n over 2 plus 1 distinct frequencies. Okay. All right. So that's good to know. Now, what is the point of all of this complex exponential stuff? Well, it's this idea that if you have two frequencies k and l, such that k and l are not the same, so k is not equal to l, then I'm gonna claim that ekn and eln, their inner product is 0. Remember, inner product of 0 means they're completely unrelated. Two vectors have an inner product of 0 when they're perpendicular to each other. So because this vector and this vector are in no way related to each other, they're as opposite as they can be, their inner product of these two vectors would be 0. And so what we're saying is that if you have different frequencies, remember, k and l are always integers. So k and l belong to the set of integers. So they're like 1, 2, so on. If you have different integer frequencies, I can guarantee that their inner product will be 0. Okay, it's good. Okay, let me just do a follow up to that. If k is if these frequencies are the same here, so if we take ekn inner product with ekn, then I'm claiming that we get 1. Okay, and this is good to it's okay, we can practice the calculation for this, but let's show, we need to show both of these things. So our goal is to show this, that okay, when k and l are different, I'm gonna get 0 as an inner product. We also want to show that when we have the same, we're inner producting the same signal, it equals 1. And by the remember that the definition, the inner product of a signal with itself, is the same as that signal's energy. So we're also claiming that ekn has unit energy. So let's first we can do either part first, but let's first show this part. So let's call this part in pink. So we want to show this part. So we want to show the inner product. We want to start with the inner product of ekn with itself. Right, let's use the definition of the inner product, which says that this is the sum from n equals 0 to big N minus 1 of ekn. You take the first signal and then you conjugate the second signal. Okay, that's the definition of the inner product. It's the first signal multiplied by the conjugate of the second signal, and you do that over each element of the signal. Okay, well, we know e to the ekn conjugate is the same as, so it's e minus 1, ekn, and then we just showed that ekn conjugate is e minus kn. And then so what do we get? We get the sum from n equals 0 to n minus 1. I'll write the whole thing out. ekn is e to the j 2 pi k little n over n times e to the minus j 2 pi k little n over n. And then as you can see, this whole thing becomes e to the 0, which is just 1. So, I forgot the most important thing, which is that in front of each of these okay, it's not the most important thing, but it's important here. This is the reason we have actually 1 over root n's in front of all of these, which I forgot about. But you have 1 over root n's before both of the signals, right? So 1 over root n, 1 over root n, 1 over root n times 1, wait, what's going on here? Oh, okay. That the 1 over root n doesn't come there. The 1 over root n comes when we go from. Sorry, I was speaking for a sec. It comes from when we write ekn as its definition. It has a 1 over root n in it, and e minus kn, by definition, has a 1 over root n. So as you can see, those come over into the front, and we can pull them out. That becomes 1 over big N in the front, and then inside we're left with the sum from n equals 0 to n minus 1, and these things are all just 1, right? Because you multiply them, it becomes e to the 0, which is 1, and so this becomes adding 1 to itself n times is n divided by n equals 1. So that's kind of the reason, the whole reason why we put this 1 over root n. It's so that the energy of our signal itself is always 1. Okay, so that's good. We prove the first thing. The second thing we want to prove is a little bit more involved, so let's call it the yellow part, okay, which is that if k and l are different, then we want to show that we want to work with this EKN, ELN thing. Let's start with the same thing, right? The inner product is defined as sum from 0 to n minus 1 of EKN, and then it would be ELN conjugate, but I'm going to skip a step and just write that directly as E minus LN. And then I'm also going to skip a step and pull out the 1 over root n that'll come in front, because this will have a 1 over root n, this will become a 1 over n, so that's going to, 1 over n is going to come out, and then EKN is going to become e to the j 2 pi kn over n. This one's going to become minus l over n, so this whole thing becomes, when you multiply them, e to the j 2 pi k minus l n over n, okay? And the trick here is, again, we want to prove that this value is 0 if k and l are not the same. So the trick here is to actually rewrite this as, I'm going to pull out this n from here, and I'm going to rewrite it as a power. Okay, because that's exponent rules, we can do that. And if you notice, this whole stuff here is just a constant. It's all constants. There's the sum is dependent on little n's, and all the little n's are in the power, so this whole thing is a constant. So this is actually a geometric series, right? Geometric series are of the form, so a break geometric series are of the form summing from n equals 0 to big N minus 1, a to the n. So they're of the form a to the 0 plus a to the 1 plus a squared plus all the way a to the big N minus 1. This is exactly what we have here. We should know from whatever algebra, whenever you took pre-calculate or something, that the sum of the geometric series, so this whole thing, is equal to, there's a formula which says it's 1 minus a to the big N over 1 minus a. So we just apply that here. We're going to say, okay, I'm going to take u. Okay, I can't do that. How do I do this? Okay, and I'm going to take this and I'm going to say, okay, this is equal to 1 over n times the sum from little n equals 0 to big N minus 1 of, this is my a value, so it's going to be 1 minus e to the j 2 pi k minus l over n, 1 minus that to the power of n. Sorry, I forgot one more to the power of n. So 1 minus a to the power of n over 1 minus e to the j 2 pi k minus l over big N. Okay, so what's important is that let's ignore the bottom for now. Let's just look at the top, right? What is the top equal to? Well, these n's cancel out. So it's equal to 1 minus e to the j 2 pi k minus l. Exactly, okay? And if you think about it, k and l are all numbers. They're integers. So k minus l will also be an integer. So what we've done here is we're taking, this is equal to 1 minus e to the j 2 pi times k minus l, right, up here. And k minus l we said is an integer, so that's the same as an integer n. And we know that e to the j 2 pi is 1, and so this is 1 minus 1 to the n, which is always 0. Okay, so the numerator is 0, so that means that this whole expression is always 0. The tricky part here is what confused me when I first saw this proof is, okay, why can't I apply that same logic here? Why can I not say, okay, isn't the bottom also going to be 0 then, and then we'll have 0 over 0? So if I take 1 minus e to the j 2 pi, and I write it like this, and I say, hey, I'm taking that to the power of k minus l over n, and so e to the j 2 pi is just 1, right? But look at the difference between the powers here. Here, my power is k minus l, which is always an integer. Here, my power is not an integer. So at this step, it doesn't matter, right? Because we know 1 to the power of anything is 1, but not necessarily, because look at where it comes from, right? E to the j 2 pi means rotate around the circle pi, 2 pi times, and that point is where is our answer, right? So if we take e to the j 2 pi an integer amount of times, well, we take it 1 time, 2 times, 3 times, we're good. We're still going to end up here, right? But if this number is not an integer, then we might be going like fractionally around 2 pi. We might not go all the way, or we might end up here. So there's no guarantee that we end up at 1. So that's the difference, right? Here, we know n is an integer because we know k minus l will be an integer, so we're going an integer multiple of 2 pi around the circle, right? Versus here, this could be a fraction, so it doesn't, the math won't work out like that. We can't guarantee that this whole thing will be 1, okay? In fact, it is only 1 when k equals l. So this whole time, for this whole proof here, we have been assuming that k does not equal l, and then we get 0. Well, ask yourself, what happens if k equals l? If k equals l, then this top thing becomes k minus l, this becomes 0, this becomes 0. So we get 1 minus 1 over 1 minus 1, so that's 0 over 0. So it's indeterminate. So we can't use this geometric series idea when k equals l. When k equals l, we go up here and we say that, okay, when the two frequencies are the same, we get 1. Okay, we get an inner product of 1. So after all that, the idea is that this function, the inner product between ekn and eln, okay, we can literally define it as it's going to be 1 if k equals l, and then it's going to be 0 otherwise. Okay, and this definition should remind you of something, is one of the things we talked about in the first videos, which is it's actually a delta function. So I'm going to write, the best way to think about this is it's a delta of k minus l. Okay, what does delta mean? Again, anytime you see delta of something, it's going to be value 1 when the something equals 0. So whenever what's inside, when that equals 0, it becomes 1, and it becomes 0 elsewise. So anything else, it becomes 0. So as you can see, this delta function, right, when k equals l, we're going to get 1, which makes sense because we said when they're the same, the inner product is 1, and when k is not equal to l, we're going to get 0. So all that, what's the big deal? Well, what we've shown is that the complex exponentials, ekn, right, if we take k of k to be those important n frequencies, so negative n over 2 plus 1, all the way up to 0, all the way up to n over 2, okay, they form what we call an orthonormal basis, okay, of the signal space. So what does this mean? I don't know like what the linear algebra background is, but I'm going to pretend that you've never heard of this stuff. So the best way to think about it is think about R3. Think about the 3D plane. So we have a y, we have an x, and we have a z, right? What are the basis vectors we choose, right? In multi, you learned that this is our I vector, which is 1 this way. This is our j vector, which is 1 this way, and then k vector goes in the z direction like this, right? Why do we use ijk as such? We could have chosen, so even in the 2D plane, right, instead of using like I to be this and j to be this, we could have said, hey, what if this is I and this is j, right? And those two, any combination of those two can still make any point in R2, but intuitively we think the green ones are better because they're more unrelated, right? This I takes all the x into play, and this j takes all the y into play, and they handle the x and y's on their own. So the idea is that if our basis vectors can be perpendicular to each other, that's the best. That's what we want, right? And as you can see, our EKNs exactly do that, right? They're all perpendicular to each other because their inner products are 0 when they're different, right? So you can think of one vector as being E0n, then another vector as being E1n, and then the third vector will be perpendicular to both of those, E2n, and so on. We've now created our basis of vectors or signals that are all perpendicular to each other, so they have no relation to each other. And that's the orthogonal part. The normal part comes from the fact that each one of them has energy equal to 1. So the energy of each of the signals is equal to 1. So it's similar to how here we defined I, right, to be 1, 0, 0, so that the magnitude of I would exactly be 1. We could have called it 2, but just for convenience, we made it exactly a magnitude of 1. Okay, so that's kind of that's the end of this unit. The key idea is that these where did it go? These complex exponentials are nice because they're all orthogonal to each other and they're all normal, so they all have magnitude of 1. That's going to help us do analysis with them. It's going to set up the basis for the Fourier transform, the discrete Fourier transform. And if you understand that all we're doing is we're taking our signal space and we're breaking it down. So instead of we can write everything, just like with R3, we can write everything as a combination of these three vectors, right? In our signal space, we can write any signal as a combination of these EKNs. And that's the big idea. Okay, bye-bye.